So this is the first video to techniques on finding derivatives. So this is very exciting. This is what calculus is all about. So these are our first two techniques, our first two rules. And we have that the derivative of a constant is 0. Oh, what a surprise, right? So what does this mean? So if we have our graph like this, having a constant, this just means that y is equal to c, to some constant. So we have a horizontal line. Well, you know that the slope of a horizontal line is just 0. So delta y over delta x is just 0. There's no rise, but a lot of run. So for any x, delta x, delta y is just equal to 0. And so our slope is 0. The definition of derivative is just the slope of the line, or the slope of a tangent line. In this case, the tangent line is just basically the line itself. So the derivative of a constant is just 0. However, this becomes very useful because, as I already kind of mentioned in one of the previous videos, when you have g of x plus h of x, and you want to find the derivative of that with respect to x, well, that is just g prime of x plus h prime of x. And let's say that h of x is just a constant, well, you know that actually h prime of x will just be 0, and you're only worried about finding the derivative of g of x. So I guess it's kind of useful. Well, I don't guess. It is very useful. And next is the power rule. This is a little bit more exciting than the constant rule. And so, as you might recall, we already found that the derivative of x cubed with respect to x is 3x squared, and that the derivative of, x cubed. Did I say? Yeah, the derivative of x cubed with respect to x is 3x squared. I'm not sure if I mentioned something wrong. If I said something wrong. And the derivative of x squared with respect to x is just 2x. Well, we actually can see a pattern here. You can see that our exponent turns out to be our coefficient in our derivative, and the exponent decreases by 1 in both cases. So here is a 1 actually. And so we can just generalize this rule. And the derivative of x to the n is just n times x to the n minus 1. And so let's work this out. So if we have x cubed, well, n is equal to 3. And we know that d of x to the n is just nx to the n minus 1. So the derivative of x cubed must be 3 to the x, 3 times x to the 3 minus 1, which is just 3x squared. You can try this out for x squared. It all works. But something that we actually tried before is if we say that f of x is the square root of x, and we find the derivative of f of x, we also found that to be 1 over 2 times square root of x. Well, the square root of x is just basically x to the 1/2. So according to our rule, well, it actually is in the form we need it to be in. So we say that n is equal to 1/2. So d of dx of x to the n, yes, nx to the n minus 1. So we have 1/2, right? Because we brought the exponent down, times x, and then 1/2 minus 1. 1/2 minus 1 is just negative 1/2. So d So the derivative of x squared is just 1/2 x to the negative a half. Well, x to the negative a half is 1 over square root of x. And so we can just rewrite this as 1 over 2 square root of x, which is exactly what we got before. See? It's the same thing. So it actually works for any problem that is in this form, x to the n. Actually, what is a constant? So a constant is just some value times x to the 0. And we will see what happens when you are multiplying two things, but for now, let's just say that c is equal to 1. So if we have x to the 0, what is the derivative of that? Well, that is just 0 times x to the negative 1, which is just equal to 0. So here we just proved that for c is equal to 1, yes, this is true that based on our rules, the derivative of that is just 0. We will see that what happens when you're multiplying two things, and so we will be able to generalize this way of finding that the derivative of a constant is equal to 0 to more values than just to c is equal to 1. We would actually show that this is true for any c where c does not depend on x.